The end. Okay, now the session is being recorded. But now I'd like to introduce today's speaker. Stephen F. Smith is a research professor of robotics at Carnegie Mellon University, where he leads the Intelligence Coordination and Logistics Laboratory. Smith's research focuses broadly on the theory and practice of next-generation technologies for automated planning, scheduling, and control of large multi-actor systems. He pioneered the development and use of constraint-based search and optimization models for solving planning and scheduling problems, and has successfully fielded AI-based planning and scheduling systems in a range of application domains. His more recent work on smart traffic signals, which combines concepts from artificial intelligence and traffic theory, led to the development of surtrac, an innovative decentralized system for real-time urban traffic signal control. In 2015, Smith co-founded Rapid Flow Technologies Incorporated to commercialize the surtrac technology. It's now deployed in over 20 North American cities, and in October 2022, Rapid Flow Technologies was acquired by Myovisions Incorporated. And Smith's current work in this area focuses on making smart traffic signals smarter and safer through integrations with real-time traveler-to-infrastructure communication, and on using these advances as a basis for establishing more sustainable transportation infrastructure models. He's a fellow at the Association for the Advancement of Artificial Intelligence, and in 2022 became president-elect of this association. Please help me in welcoming Professor Smith.
I hope I can live up to that. Those of you who look closely might notice I changed this title slightly. I haven't changed the focus of the talk, but as I was thinking about, as I was developing the talk, my group for the last 5 years or so has been evolving a technology, a smartphone app for supporting safe intersection crossing for pedestrians with disabilities. And so I'm going to kind of go through a lot of what I talk about will be explaining that technology, how it's evolved, and I will be talking about along the way about a project that we did fairly recently in sort of trying to broaden the focus and looking at other aspects of the complete trip. But I thought maybe this title would be a little bit more toward what the talk is going to say. To start out, we're interested in supporting pedestrians with disabilities as they interact and navigate through the world. USDOT, I guess they're the ones who've kind of coined this phrase, complete trip. But the basic idea is that an individual should be able to travel from origin to destination without gaps in the travel chain. And what is meant by a travel chain is, you're going to go somewhere in an urban environment, for example. Quite often you'll sort of navigate to a bus stop, catch a bus, go somewhere else around town, get off, do your thing, and so forth. So this is a very challenging activity for persons with disabilities, and in fact, we're of the belief that we can provide some useful kind of technology support. In fact, the genesis of the PedPal app that I'll be describing today really came out of a Federal Highways Administration program called ATRI, Accessible Transportation Technology Research Initiative. And that was really aimed at, broadly, that initiative was aimed at sort of exploring technologies that might support various aspects of the complete trip. And in fact, as we go along here, we'll see that we've in fact interacted with some other participants in that program towards integrating these concepts. So the outline of my talk, I'll first give an overview of the PedPal safe intersection crossing technology that we've built and we're continuing to evolve. Then I'll move to this expanded project that actually, was it Safety 21 or, anyway, it was
You started with
they had
mobility.
a Mobility 21, right? It was one of their so-called big ideas projects, which was, you know, a little larger funding than usual and involved sort of a host of different faculty around the university. So I'll talk about that and what came out of that. And then I'll talk about our more recent focus, our current work that's focused on really getting this technology out in the world and lowering the, I'll explain what I mean later, but lowering the barrier to widespread deployment so that we have a better chance of getting it out. I'll conclude, or I'll finish by describing some short-term deployment opportunities that we're pursuing, and then finally talk briefly about the DOT's current intersection safety challenge, which we're a part of. So the basic concept of PedPal is safe intersection crossing for pedestrians with disabilities. The basic idea is a smartphone app that allows pedestrians to communicate directly with the traffic signal system and, in fact, influence the traffic signal system to their advantage. So as far as capabilities, the most basic kind of capability that is provided is you have a personalized crossing time. So your app knows how fast you travel, you know, whether you're navigating with a stroller or walking with a cane or whatever. And it can communicate that to the intersection, how much time you need to cross the intersection that you arrived at. So when you do get to some crossing signal, you'll have enough time to cross comfortably. The app can also actively monitor you as its user as she's crossing, and it can detect, you know, if you're taking longer than usual, that it can interact with the traffic signal system and dynamically extend the green times if you're having trouble. Maybe there's snow on the ground which is making you move slower than you normally would, or whatever. You can also, through communication with the traffic signal system, anticipate arrival time at the intersection, and attempt to sort of expedite your movement through the intersection. So if the traffic signal system can anticipate your arrival, it can work the signal timing plan so that you get the green without too much undue delay. And then finally, you can do other things like signal presence to oncoming vehicles. You know, as you move in, as the pedestrian moves into the intersection, we can use connected vehicle technology to communicate your presence in the crosswalk to an approaching vehicle that has the radio capability. So our technical approach, I've sort of given this away, but our basic idea is to exploit so-called connected vehicle technology, radios that are going into cars, or the roadside units that are placed at intersections to allow the pedestrian to communicate directly with the intersection. And to provide all these real-time capabilities, our focus has been integrating with surtrac smart traffic signal system. For those of you who are not familiar, it was mentioned a little bit in my introduction. Surtrac is a real-time traffic signal control system focused on optimizing traffic flows in urban environments, particularly. It operates in a completely decentralized fashion. Each intersection that has its own local process. We put a computer at every intersection that sort of monitors its own traffic. And this is vehicles and pedestrians, all modes of travelers. And then essentially programs the traffic lights in real time to set the green times so that currently we're minimizing cumulative delay. So that technology was developed originally in my lab at CMU. In the field, it's been very effective. Sort of the typical kinds of results we get are a lowering of travel times by 26%, not because vehicles are moving faster, but they're stopping 30% fewer times. And when they do stop, the period of their idling is reduced by 40%. So this, as was mentioned at the beginning, we commercialized this technology in 2015, and it's now been acquired by a larger company, Myovision, in the transportation industry space. But we're now deployed in 20 North American cities. So with that in mind, that we really rely on SureTrac's real-time capabilities, the ability to adjust the signals in real time, that allows us to actually provide a lot of these capabilities. So I think I have 2 slides here. Yeah. So this is this is kind of how it looks out in the world, and I'll explain a little bit about this. But in the 2 pictures in the center here is the traffic cabinet that you have at every intersection. We put a computer in there, and that's what runs our traffic signal control system. And then at the intersection itself, we have a variety of sensors here. There are cameras. This is in East Liberty. And then this device on the pole here is called a dedicated short-range communication radios. Originally, it was envisioned that these radios, this DSRC radios, would really be the foundation for connected vehicle technology. As conditions have emerged over time, that DSRC it's still out there, but the world seems to be moving more towards 5G communication with telephones. One problem with DSRC is that there is no chip that you can put in a phone. That's just not big enough a demand to make it economical. So when we started out PedPal, we started out by using this, if you can see this DSRC, it's a DSRC radio sleeve, they call it, and it attaches, the phone attaches on the front of it, and the phone talks to the device through Bluetooth, and then the DSRC communicates with that. That turns out, as you can imagine, this thing, I should have brought it actually, it's pretty clunky. And we, even in the first year of sort of testing with real users, it was more trouble than it was worth. In the second year of development, we switched to, more of a, cellular communication to the cloud from the phone, and then Wi-Fi or cellular into the, so we have a cloud server now that works. And so both of these are supported, but it's rare, I think, that you see DSRC capability. In the meantime, though, DSRC provides a lot of work has gone into standardizing a set of messages that you would communicate back and forth from the intersection to a vehicle or the intersection, in our case, to the phone. A couple of messages that are very important to us. There's a map message that when a user arrives at the intersection, communicates basically the geometry of the intersection, how many lanes are in each crossing direction, how wide, what's the width of each lane. where the crosswalks are, and so forth, that allow you to sort of do the computation of how much time it'll take to cross. And there's another important kind of message. It's called SPAT message, signal, phase, and timing message, and that communicates essentially where you are in the current cycle of greens and how much time is left in the current phase, when I expect the crossing phase to be green, and so on and so forth. So that gives you the app real-time information about about so it can instruct the user when to cross and all of that. The app itself, we've taken a universal design philosophy to it. We're obviously this kind of device is going to be more useful to some users than others. Probably the mobility challenged and walker kind of thing, and vision impaired individuals are probably the most benefit. But we provide support for all. There are multiple interaction modalities. You're seeing a display there with some settings, and when I show you how it runs, we'll be using the visual display. But it's also interoperable with voiceover, and there's also haptic ability to signal haptically with vibrations. And we've chosen it to operate on iPhones at this point, but we're interoperable with the native iPhone accessibility features. So all that, as we've had experience, doing field tests with volunteers from the local disability community, we've actually find they're pretty sophisticated at using, on average, of using these sort of native features, and it's pretty impressive. Here's how it works. Here's how I would cross the street with so I approach that. I get the map and SPAT messages. Boom. Now I can give the user a choice. Here are the possible crossings. It's recognizing at the corner. I could pick Cypress, which is currently green, has 13 seconds counting left, or select. So I think here we selected a future phase, and so it's telling us don't cross. It'll actually go to sleep and wake up 5 seconds before it's time to go, to sort of get the user going, and then once the green light turns, it gives the okay cross. As you cross, it's giving you a countdown information. This is all adjustable. It could be really annoying to hear every second. You could set it so you hear every 5 seconds, but that's all customizable. And then, and so then you do it. Now you've completed that crossing. Now it's presenting you with where you could now cross. So if if you're going 2 sections, you're now ready to go to the next one. You can pick it and then take off when you get it. This is kind of just a static showing of the sequence of screens that you do as you're interacting. So as you're approaching an intersection, at some point you get in range and you start to hear the broadcasting from the intersection with the map and SPAT. Then you can present with options. If the user picks a future phase, say I want to cross Center Avenue, it'll give you the wait signal until it's time. In this case here, when it says extension granted, that's really the bigger amount of time that you're going to get to cross, that would, as opposed to what's normally set by the traffic signal controller. And then if the information is available at the intersection, you can kind of retrieve additional information. Maybe it tells you something about how to orient yourself this is talking about where the curb cuts are and how to align yourselves, and then go. We did a few years ago now a user evaluation, sort of a formal user test. We enlisted 12 volunteers from the local disability community. Those kind of broke down into the following categories. The big emphasis was on vision impaired, mobility challenged, and deaf individuals, and really it was sort of aimed at those groups that would that would need we'd expect might get the best benefit out of the technology. And so for each of these 12 volunteers, we carried out a series of crossing tours on a subset of intersections, actually right around Shadyside Hospital over in East Liberty, Shadyside. And we did these tours both with the app and without the app, so you sort of have this comparative kind of thing. We have computed, we have quantitative results we could show, but overall, as we expected, you get differential benefit. Certainly that was observed. If you're a sighted person and you're using a motorized wheelchair, that's probably you probably don't have as much. Well, you won't have as much difficulty crossing the intersection. But overwhelmingly, we got positive response from all the participants. It was even those who could. Was not directly benefiting them could see the benefit in general but this early prototype, the Achilles heel of this early version of the app was really its localization capability. When you're, there is a GPS in here and a number of other sensors that can be put together to do localization, to tell you exactly where you are. But out in the intersection in urban, it doesn't do a good job at all. You could, from time tick to time tick, you could be in the middle of the intersection, you could be on one side, you could be on the other. So that was really a problem, with the early version, and we enlisted the help of a graduate student from another group that works on indoor Bluetooth sensing. We could put Bluetooth sensors up there to help it, but actually the Bluetooth isn't very reliable either in that space. Out in the urban canyons. What did help us, though, the advent of ultra wideband radios has really provided us with a solution to that. When we did our user test, we sort of jimmied it so that we would signal to the phone when they arrived at the corner, so we didn't have to do any corner detection. And then we asked the user to tell us when they completed crossing. But with the advent of ultra wideband radios, now it's kind of a game changer. With these, we're able to get 2 to 5 centimeter localization accuracy. And our current model is we augment the infrastructure to put minimally a Bluetooth beacon at each corner of the intersection. And iPhone 12 and above all have ultra wideband radios embedded in them. So we can communicate with the intersections to get very precise distance information. And so that then with that kind of thing, automatic corner detection with ultra wideband beacons infrastructure, it's now a simple solution. We just do what's called geofencing. Sort of have a beacon at each corner. We define a radius around that beacon, and we can detect precisely when the user moves into that circle, and that's the signal to to the system that we've arrived at the corner. And these beacons are constantly communicating the distance to the phone. So that works great. The cost of these things is pretty negligible. I mean, think air tags cost, this is the same technology, $20 to $25, I think. Or the ones you would put at the intersection, a little more than that, but not much. So that's great. The other thing that these beacons allow us to do are things we couldn't do before. We can also now detect or think about detecting movement outside of the crosswalk. So if I'm a vision impaired person and I'm crossing, now with this kind of precision, we can monitor progress, and if we notice that the user is moving outside of the crosswalk, we can send a haptic signal or something to get one vibration while you want to start moving to the left, to the right, something like that. And we've had a student who looked at developing an algorithm for doing this trajectory prediction, and demonstrating the potential of this in simulation. And you can see the basic algorithm sort of tracks the ground truth pretty well. She also implemented a corrective trajectory if you wanted to give more information to the user, and that also seems to work pretty well. So this is a great new capability that we can provide. So here's the kind of current system architecture. I showed you this picture a little while ago, but now we have at each corner, this is a particular kind of beacon that we've been working with, experimenting with. And then we have the cloud server connection to the surtrac and the phone. So 2 years ago, I guess, we embarked on this big ideas project, creating and integrating solutions to enable the complete trip. So the idea here was, our goal was really to build a complete trip app. That was the vision. We didn't expect that we'd get totally there, but we were looking at integrating the following kinds of capabilities. There's a local company in Pittsburgh, Pathview, who does sidewalk mapping and accessible routing. So you notice places where the sidewalk, they go through the city, they notice where sidewalks might be damaged, cracked, maybe the areas or roads where there are no sidewalks and you have to go out into the street, collect all that information and then use that information to do routing. I call it here pedestrian friendly routing, but not necessarily the fastest way, like maybe Google Maps would typically take you, but the most accessible way. So a way that would sort of avoid construction. And their map database is designed to sort of support sort of transitory things. So if you had a construction site there for a few weeks or something like that, that could be entered into the database and so forth. And they have an app that provides crowdsourcing support for that. Our safe intersection crossing app, PedPal, was, and then a couple other capabilities. One was this notion of real-time, essentially autonomous wheelchair assist support, so that, for example, if you're moving in a wheelchair, these would be a motorized wheelchair, but if you'd like the system to navigate curb cuts or there's some sort of challenge there, you can turn that over to the thing. So real-time obstacle detection and autonomous assist, that was another set of capabilities that for wheelchair users would be useful. And you can also imagine that you could put sensors on the wheelchair that could detect new problems that mapping database should know about. And then finally, coordination with public transit and this is written over, but a vehicle approaching vehicles. So that was sort of the vision. As we went through the project, we kind of ended up, we kind of split into sort of two tracks. You know, one where we expanded PedPal. I've called it PedPal Plus here, but I don't know if that will ultimately be the final name. But the basic concept here was integrating PedPal with this accessible routing capability provided by PathView. Another thing that we also provided and demonstrated was the ability to communicate presence in the crosswalk to approaching vehicles that were connected, you know, so that they can they're aware of the pedestrian in the crosswalk and you know, can take action as required. We also, although we didn't get all the way there, it certainly is possible to go the other direction too. I think if you have a vehicle, well, we were working with an autonomous vehicle company, but if you have a vehicle that has sensors on board, they can kind of look around themselves and sort of give estimations to the intersection of how much traffic is flowing their way. Or to the phone. So let me see if I can. And just play this for you. This is a summary video that we made of this PedPal Plus.
Hi, I'm Steve Smith. I head the intelligent.
I'm not sure you can hear that online or
My
not.
lab really focuses on next generation technologies for automated planning, scheduling, coordination, and optimization. One principal application area of our work has been smart transportation infrastructure for urban mobility. Real-time adaptive traffic signal control. More recently, we've been focusing on support for pedestrians, particularly pedestrians with disabilities in crossing signalized intersections. We developed a smartphone app called PedPal, which interacts directly with the traffic signal system at the intersection.
Hi, my name's Eric Sinagra. I'm the CEO at PathView. PathView is a Pittsburgh-based startup spun out of the University of Pittsburgh. PathView focuses on aggregating sidewalk data for improved mobility and accessibility. Our role in this project is to provide sidewalk data for navigation purposes. Our API provides the AV directions, step-by-step information on getting down to the intersection so that PedPal can pick up from there and help the pedestrian safely cross the street.
Penn Avenue and Highland Avenue Southwest.
Our navigation API knows whether there's a sidewalk on one side or the other. From there, the algorithm returns step-by-step directions along with a route for the pedestrian.
Approaching the corner, select street to cross.
And it bases that route off of their custom preferences,
At the corner,
the sidewalk location, and the conditions of the sidewalk.
Center Avenue, waiting. Okay to cross, 23 seconds Center Avenue.
The app can also monitor and track progress. If it detects that you're moving slower than usual, you can request additional time.
Select street to cross.
The app knows how fast you travel, so it can request that when you do get the green, you'll be sure you get enough time to comfortably cross.
Extension granted.
We also have the capability to, if they're approaching one of the sides of the crosswalk, alert them and take some corrective action.
The longer-term vision for this partnership between PathView and CMU is to integrate the two technologies together, working towards what is called the complete trip. where going from A to B, you can know that the route is both safe and accessible for the pedestrian, taking into account information such as what PathView offers and what PedPal offers, and even other information about transit and accessibility information along the route.
It's great to have Simon here. So I guess Simon doesn't.
So the one thing you didn't see in that video was any interaction with vehicles. We worked with the company Argo AI in demonstrating that we could communicate with the vehicle, and the vehicle could react to the pedestrian being in the crosswalk, and successfully did that. So a couple weeks before we made the video, Argo went away. So they weren't in the video, but we were able to demonstrate that as well. You know, I said on the more enabling technologies front in this thing, there was also work done in autonomous wheelchair navigation, and so one corner of the program, Gino and Ji Zhang leading the effort, they developed the ability to kind of navigate with a learned traversability model, sort of learning what, you know, whether sidewalks, stay off the grass, those kinds of things. If you encounter snow, maybe, you know, avoiding that. And they were, you know, their final demonstration at the end of this project was to take an autonomous traversal for the wheelchair from Newell Simon over here to the bus stop on Forbes. So it was an interesting and challenging kind of demonstration. So, you know, the automated technology for wheelchair, I mean, that's not going to happen tomorrow, but, you know, you can imagine in the future that's an area that can be built into. We also, another corner of the project also worked on dynamic object recognition using a technology called a light curtain. And a light curtain is just sort of visualized there. It detects the presence or absence of objects at specified distances, so very accurate. So one thing that allows you to do, what they were able to demonstrate was that you could, if you dynamically and adaptively sample at different distances, you can detect small objects and fast-moving objects that are coming towards you. So again, another enabling kind of technology that you would need, you know, to navigate in a crowd. If you imagine, you know, a busy urban street. What we're currently, our current project, what I'm calling PedPal Lite, is really aimed at lowering the barrier to deployment. And specifically what I mean by that is, you know, our idea always was, and still is, that we would give away this technology to a municipality that purchased surtrac traffic signal system. But there's a wide variety of, you know, the vast majority of intersections don't use any kind of smart, intelligent thing. And you know, how can we get, well, not only to mention that surtrac is a sophisticated and relatively expensive system. You know, I think, you know, the pricing is like $20K an intersection. And so, you know, to get a wide coverage is a pretty big bill. So anyway, the sort of goal of this approach is to develop a version of PedPal, which we, you know, kind of currently calling a PedPal Lite capability, that doesn't rely on surtrac. It kind of decouple it from the traffic signal system, and instead just interact directly with a hardware controller so that immediately could be usable by, conventional traffic signal systems. And how do you do that? I mean, there's a million different controllers out there. It's a potentially really challenging task to build interfaces to every one. What we've chosen to do as a starter is to utilize a standard, the NTCIP, a standard controller interface, and most modern computers or modern controllers use this kind of support this kind of interface, and so to maximize the number of controller types that we can kind of easily go at. Otherwise, we just have to build them as we go. But we're currently engaged in this. What this amounts to is we lose a little capability. We lose the capability to maybe do real-time extension of the traffic signal. But the basics, you can all, the basics of specializing the crossing time to the user, and plus the newer capabilities like being able to detect movement outside of the crosswalk, so forth, is all doable without the smart signal. So toward that, or sort of as a follow to that goal, we've been interacting with Sacramento County, and they currently have a proposal pending with DOT, attain one of the build back better infrastructure bills to work with us to harden and carry out a 2-year pilot test of this PedPal Plus capability. And by that I mean to build this combined app that combines wayfinding, navigation, route planning with safe intersection crossing. So this will be our first opportunity, assuming it gets funded, to utilize the PedPal Lite capability to integrate with their existing controllers. So that's the plan. And another aspect I didn't mention before with the ultra wideband beacons that we've been using, and by and large this is the same for all beacons at this point, rely on Bluetooth to sort of establish connections with the phone, and then you can use the ultra wideband, and that doesn't really work in our setting. So one of the vendor that we're working with, a company called Estimate, is working with us to build a version of their beacon that we can directly power at the intersection. So, and I think that'll be the future, way to deploy this. That there's power in the cabinet, there's power at the light poles if they're around, and so that'll be the approach we take here. This is just a picture of where they are wanting to deploy, and these yellow bars are the sort of corridors that we'll start out with the PedPal. But these are all, I guess it's hard to read, but these are all disadvantaged communities within the Sacramento city limits, I think. But so kind of excited about that.
Steve, where would the capital be on that?
That's a good question. I don't know. I'll have to figure that out and send you a message. Yeah. It's not. Yeah. I don't know.
Capital's right downtown.
Yeah. So that's sort of one of I think our biggest opportunity to really sort of put it. The idea is to do a 2-year pilot there, and Sacramento County will do all the recruiting and marketing to get people interested in working with it. So we'll see how that goes. The other thing I'll just end with, DOT I don't know how many of you are familiar with, but they established this competition last year called the Intersection Safety Challenge. And the first phase was really to develop a concept that a concept for improving intersection safety, particularly to vulnerable users, pedestrians, bicyclists, whatever, certainly persons with disabilities. We were part of a team that was headed by Myovision, the company that bought surtrac, and we were one of the stage 1A winners. They picked 15 winners. The prize for phase was, they didn't offer any money, but the prizes were $100K. So each of these 15 groups got $100K. Now we're moving into phase B. And this is, it was a fair amount of competition, I guess. They gave 15 winners. There were 100, I think they said 120 submissions. So who knows? But now we're moving into stage B, 1B, which the prize here is $1 million. I guess they'll move up to 5. But stage 1B is really concerned, well, they're calling it system assessment and virtual testing, but it's really about algorithms to detect, localize, and classify objects, individuals, vehicles at the intersection, and to do prediction, trajectory prediction, and detect potential conflicts. So they're generating a bunch of data, and each team of these 15 teams will get access to that data and try to do it. When I say generating data, they have a test facility or an intersection at test intersection at Turner Fairbanks, their facility outside of DC, and so they've been the last several months generating, I don't know, different scenarios and providing the sensor, collecting the sensor data and so on and so forth. And so over the summer, basically, we haven't seen any data yet, but over the summer, really, I guess from April to maybe around September, we'll first get a bunch of training data that we can use to train our algorithms and our models, and then they'll give us the test data in August or September, I guess, something like that. Anyway, in the initial phase, in the concept phase, Myovision put together a team with many players, basically. PedPal was part of that, and that will eventually be part of our concept if we ever got to the stage 2, but they also had a consulting company, Deloitte, a communications company to do the communications, and a bunch of different players. And it turns out that this phase 1B is just all focused on doing this sensor fusion and trajectory prediction. So they've come to us, and I think their plan is to go with just us and Myovision in phase B, and they were asking if we could take a bigger role in that. So CMU, I think will been able to recruit a couple other people. Srinivas is going to work on John Dolan, and Kumar from ECE is a radar expert. So we've put together a team. We're still finalizing the arrangement with Myovision, but we're looking forward to trying to win the money. So anyway, so that's all. That's basically all I got. So yes.
I was wondering, like they're building that BRT
from here to downtown?
Yeah, yeah,
Are they
yeah.
planning to incorporate any of this kind of technology in designing that?
Well, not so much, well, the city itself has a plan to expand the implementation of the adaptive traffic signal. And it would certainly, that would be part of the BRT would be part of it. The challenge there is a little different, but you know, to sort of eliminate bunching and kind of keep it running more like a subway. But it's going out to bid this year, I think, and I suspect that my vision will have a good chance of getting that since we're already here. But I haven't thought about the design so much. We've had interactions off and on with well, they're not the Port Authority anymore. They're what is it? The regional transit organization, but not with that. Yeah.
Can you speak about the security of the signals throughout the PedPal system? Well, you know, from a cybersecurity point of view, are the signals secured using any advanced?
Yeah, that's a great question. Well, we do take steps to try to minimize the possibility of somebody hacking it into it. We exchange encoded messages, and you know, we have software on our server side that kind of recognizes or tries to recognize when it's not coming from a legitimate source. And then the back end into the traffic signal system is typically a closed network, so that helps there. There's no guarantee, you know, and that's a hard problem in general. You know, we've been thinking about it, but we've taken these kind of initial steps. Yeah.
I have kind of a follow-up question to that, and that is, you mentioned the standard for communicating with controllers for the light version of your software.
Yeah.
What kind of communication mode are you using? Is it 5G? Is it?
Yeah, well,
it's all over the place with controllers.
Yeah. Well, we don't totally know the answer to that yet. I mean, because some, well, the one I know the most about is Econolite, because that's what Sacramento County has, and that's what we've been looking at. But they have a device that does the VDI message generation, and that would be, you know, just.
That's standard for all of the Econolite controllers?
Yeah. I mean, our original idea was there's this public domain software, the VDI hub, that we use now. But if that's available, and that I guess will vary from controller to controller, but that's all communication that's happening inside the cabinet. Even if it was our processor, you know, if we don't have a device from the controller company, then it's going to be our device that's running VDI hub. So the only communication, well, the communication to the cloud server, typically if we're talking to the intersection, we can go through a closed network. I guess in the worst case, we'd have to put a phone in the cabinet, but yeah, I don't think that's necessary in too many places, but
Okay.
yeah. Anything else? Great.
Thank you so much for sharing your work. I'm not sure if I can say this, but that was definitely my favorite so far. This is really, really cool. But thank you everyone for attending today. As I mentioned earlier, this was recorded, so if you feel like rewatching it, it's up on the What's Happening page on the Safety 21 website. It'll probably be uploaded later today. For students who are really interested in getting more involved in transportation, those two guys in the back will be your best friend. They can talk to you about Transportation Club, or you can look into it on Tartan Connect. And our next Smart Safety Connection seminar series will be on Friday, April 19th, featuring Professor Justin Starr from the Community College of Allegheny County. So watch your emails for an invitation. Thank you.